Okay, fantastic. So this is a good talk to follow up John's because different set of questions, but very similar set of motivating phenomenon. So this paper is joined with Erik Madsen. Right, so online platforms and data brokers are now actively tracking and recording a whole range of consumer activities and producing new measurements of everything from how many friends you have on social media to how often you change residences, to even potentially how many hours you spend playing video games. Okay, now this new data is increasingly available to firms and organizations, as John pointed out, and correspondingly, regulators are increasingly concerned about various possible new use cases of this data. So for example, banks might use this data to predict whether an agent is creditworthy, and firms might use this data to predict a worker's productivity at a new job. Okay, now these are still very much emerging applications, but they're ones that have attracted a lot of attention. So there was a recent EU regulation draft that was circulated, which labeled these applications, among a couple of others, as high risk. And they point to not just the possible privacy concerns, but also the possibility that these forecasts might in some way distort behaviors. Right, so to understand when and how to regulate the use of this new data, we need to first understand the economic implications, which are many and quite complex. So there's been some very nice recent work in this direction, but we're still very much in the early days of understanding this. Okay, so our paper focuses on those implications within markets where moral hazard is a key issue. So specifically, we have in mind settings where agents choose a level of effort which is hidden, but potentially productive. And the main reason that agents choose to exert that effort is not contractual. It's instead some sort of reputational payoff. You exert effort in order to improve a market's perception of your quality. And now naturally, big data creates all this new information about agents that can also be fed into these forecasts. And what we ask is how that new data then is going to impact agents' effort choices and ultimately welfare. Okay, so let me just jump straight into the model. So we're going to be building upon the classic Holmstrom career concerns model, which is a model of reputational incentives for effort. So let me just begin by quickly reviewing that model. Okay, we're going to work with a variant of the model where an agent participates in a market across two periods. The agent has a type theta, which is unknown both to the agent as well as to the market. In period one, the agent is going to choose a level of effort E, which is hidden at some cost. And that level of effort, along with the agent's unknown type, along with an independent shock, epsilon, are going to jointly determine the realization of an observable outcome. Then in the second period, the market is going to observe that outcome and use it to update its belief about the agent's type. And the agent is going to receive a reputational payoff, which is simply the market's posterior expectation of his type. Right, then finally, the agent's total payoff is simply going to be a weighted average of this first period cost and the second period reputational payoff. So actually this reputation weight beta isn't going to play a role until I start talking about welfare. So for now, you can just keep it in the back of your minds. Okay, and what's interesting in this model is that although effort is costly to exert, agents are nevertheless going to be incentivized to do so because higher choices of effort lead to a shift upwards, an FOSD shift upwards, in the distribution of this outcome variable, which under suitable regularity assumptions on the distributions further implies a higher inference about the agent's type. Okay, so that's Holmstrom. And what we're going to do now is we're going to take these key primitives, the type theta and the shock epsilon, and we're going to pretend that these, well, not pretend, they are actually, we're going to model these as predictable from underlying covariates that describe the agent. Okay, so specifically, we're going to suppose that theta decomposes in the following way, epsilon decomposes in the following way. We're going to call these different components covariates. But we're going to distinguish between those covariates which are informative about the type versus covariates which are informative about the shock. So the first category we're calling attributes, the second category we're calling circumstances. And formally, these are all random variables. Okay, just to give you some concrete examples, if we're thinking about the labor market, theta might be something like productivity, y might be something like output. An example attribute in that setting might be something like the worker's fundamental reliability, right? That's a sort of long-run persistent attribute of the agent, which the firm might like to predict. Okay, now that naturally influences output, but output is also going to be influenced by other things that are beyond the agent's control, like potentially shocks to the industry. So those would be potential circumstances that the market would like to debias from Y. Okay, in the college admissions case, we might think about theta as being ability, Y as being the student's GPA. An example attribute might be something like the student's attention span. Again, that's relevant for GPA, but if the student happens to be undergoing some sort of illness or injury, that's also going to matter for the student's GPA, and the admissions officer might like to debias that aspect, that contributor to this outcome. All right, so these attributes and circumstances I want you to think about as the universe of everything that might be relevant towards theta and epsilon. Okay, only some subset of those attributes and circumstances are actually going to get to be measured. And that's going to be denoted by this the script J and the set script K. Right. Our timeline then is as follows. So we're going to suppose that at an initial period, the agent and the market are going to get to observe the agent's covariate values exactly for those measured covariates. Right. Then subsequently, the agent is going to choose an effort level at a cost. This outcome is going to be realized. And finally, the agent is going to receive the market's forecast, where importantly now, this forecast is based not just on Y, but also on the agent's measured covariates. Okay, now, in our model, the distribution of effort choices then across agents within a population is going to depend crucially on the family of measured covariates that are taken as an input. Okay, and we're going to think about big data then as implying an expansion of the set of measured covariates, right? So initially we had some set of attributes and circumstances that potentially was already being taken into account. Now big data is making it possible to observe and use things like, again, the number of hours you spend playing video games or what kind of news you read. Those now are added to these sets of measured covariates. All right, so just a couple of quick comments on our knowledge assumptions in this model. So we've assumed a symmetric uncertainty where, given the agent's measured covariates, the agent and the market have the same perception of the agent's distribution of type and shock. Okay, so we might ask, well, should the agent know more, right? You know all of your own characteristics. Why doesn't that lead to private information about your type and shock? And here what I want to point out is that each theta j is not literally the value of the covariate, but really the effect of the given covariate. Right, so you might know, for example, the number of hours that you spend playing video games, but knowing how that number translates into an effect on your productivity is a substantially more demanding knowledge assumption. Right, so we might actually ask the other question, which is, in fact, should the agent know less? Right, how is the agent? The firm might have a big record of agents, which allows it to learn these conditional distributions, but how is a single agent forming that perception? And here, let me just point out that first, agents only need to learn, they only need to understand the marginal value of their effort, right? You don't actually need to know those full distributions. You just need to know what would happen if you were to increase your effort. And that's something that could be learned through experience in the market. And the other thing I'll mention is that we do actually have an extension in the paper also to a case of model uncertainty, where the agent doesn't know exactly what conditional distributions the market perceives, and instead has a belief over those distributions. And the results that I'll show you for the symmetric case can easily be extended also to imply similar results in that case. All right, then to summarize our main question, what we're asking is, suppose we start from some baseline family of measured covariates. We move now to a different data environment where some larger set of attributes and circumstances is observed and used for forecasting. How is that going to change the distribution of effort in this population? Okay, so just to give you this same question in a stylized figure, here we have a population of agents. They differ in their ability. And we can focus on somebody like Mr. Green here. And we can ask, well, what is the level of effort Mr. Green would have exerted in this environment where he's grouped with everybody else versus in this alternative data environment where it becomes known how frequently people move, right? So in this case, this new covariate divides up the population now into two new subgroups. Mr. Green is newly allocated into this group of infrequent movers that changes the market's belief about his type and his shock. How does his effort level here compare to the original case? And moreover, how does his change in effort compare to, say, that of a different agent here whose value for the new measured covariate was different from his? So those are the questions that I'll be answering for you. Right, so just a quick comment on the related literature. So our paper is contributing to a recent growing literature about the economic consequences of big data. This is a very incomplete list. More specifically related to us, there's papers who look at the impact of data on consumer effort. So a couple of papers in that vein. The main difference here is that those papers treat the data environment as fixed and solve for something like an optimal forecasting mechanism within that environment. And we instead are going to be primarily focused on varying the data environment and looking at the implications of that. Okay, and then methodologically, we're building on the career concerns literature. So the closest paper here is this paper by Duotrepont, Jude, and Tirole. And the main difference here is that in that model, they think about auxiliary information as being realized after the choice of effort, which importantly implies that all agents, that people can't differ in their effort choice depending on the realizations of that information, right? Whereas in our environment, we're thinking about the covariates as being realized upfront. So then depending on the realizations of your covariates, you may in fact choose different effort. And that's actually going to be a main theme in our results. Okay, so let me just give you a preview then of those results. So what I'll show you first is that the change in effort on average in the population is determined completely based on whether the covariate is an attribute or a circumstance, okay, where the implications are in opposite directions. So new attributes reduce average effort, new circumstances increase average effort. Okay. However, if we look across agents, this change in effort may differ across agents, not only in magnitude, but also in sign. So it can be that measurement of a new covariate causes some agents to increase their effort and other agents to decrease their effort. Okay, and we're going to call this disparate impact. Okay, I'll show you a statistical condition which guarantees that disparate impact does not emerge. And then finally, we'll use these positive results about the implications on effort to go back to this initial question about the implications for welfare and when it is the case that a regulator should step in and actually ban use of that new covariate. All right, so let me just begin by illustrating some of these forces in a simple stylized example. All right, so let's consider a labor market where this Y is the worker's output. And let's suppose that the worker's type theta decomposes into two pieces. Okay, there's one part which is your residential stability, and there's a second part which is the worker's reliability. Okay. Let's suppose that these two attributes are correlated, where the first one is uniform on the interval 0, 1. So you can think about that as like a quantile. Okay. The conditional distribution of the second attribute given the first is described here. So what we see is that for all workers who are not too unstable, right? So their stability attribute here is above the bottom 5%. For those workers, their reliability is going to be uniformly distributed on the interval 90 to 100. Okay. In contrast, for workers who are really very unstable, right? So this is the very frequent movers in the population. Their reliability is going to be uniformly distributed instead on the interval 0 to 100. Right, so what this captures is that workers who have very low residential stability are both less reliable on average, but they're also very heterogeneous. Right, so this group includes people who move very frequently because of things like evictions, which may correlate with low reliability on the job as well. But it also includes people like Paul Erdos, who famously had no permanent residence, but was one of the most prolific mathematicians of all time. Okay, so this is a diverse group here. So now let's compare what happens across two different data environments. Right, so in the first, let's suppose that no attributes are observed. So stability and reliability are both not known. In that case, all agents look the same, so they choose the same level of effort, and that turns out to be 0.16. Okay. Now let's suppose reliability remains still impossible to measure, but big data makes it possible now to know a worker's residential stability. Okay. So what happens here is first that average effort declines, and it goes down to 0.11. But this reduction in average effort is achieved in a sort of interesting way, where effort for infrequent movers, so this is people above the bottom 5%, their effort level drops to 0.08. But the effort level for frequent movers, that's again, remember the bottom 5% of stability, those people exert an effort level that now rises sharply to 0.82. And by the way, in this model, equilibrium payoffs are strictly decreasing in effort. That's fairly easy to see from the definition of the payoffs. So these two statements also immediately imply contrasting welfare implications for those agents, right? So infrequent movers receive a higher payoff. Frequent movers now receive a lower payoff. So measuring residential stability in this case then leads to disparate impact across the population. And so why is that happening? So here we'll just consider a stylized representation of the example. This new covariate about frequency of moves is splitting the population up into two groups. One subgroup being very homogeneous and the second subgroup being very diverse. So if you belong to this first group, what happens is that after measurement of the covariate, more or less the market knows your type, right? Uncertainty about your theta has gone down by a lot. And for these individuals, the marginal value of exerting effort is also quite low, right? The market already more or less knows your type, so improving the realization of your outcome isn't going to substantially change what they think about you. In contrast, for people who have been assigned to this frequent mover group, now the value of exerting effort is really quite high because the market has a lot of uncertainty about what your type is. In fact, higher uncertainty about your type now compared to in the baseline where this covariate wasn't observed. So for these people now, the marginal value of effort is actually quite high. All right, so our main results then are going to just give us a sharper understanding then of these forces that we've discussed. So both this aggregate change and also this redistribution of uncertainty across the population. All right, so to simplify notation, let's actually just work with two attributes and two circumstances. So then theta and eta and epsilon decompose in the following way. And I'll show you results that compare the distribution of effort across two data environments. So in the baseline, let's just suppose that no covariates are measured. And we'll toggle on and off measurement of one covariate, okay, where that covariate is either a new attribute or a new circumstance. Okay, in both cases, we'll use the one labeled 1. So the first result applies to a class of what we call affiliated covariates. So we're going to say that attribute 1 is affiliated if theta 1 and theta 2 are affiliated random variables. Okay, we're going to say that circumstance 1 is affiliated if epsilon 1 and epsilon 2 are affiliated random variables. Okay, so just to remind you, affiliation is a strong form of positive dependency. So this implies that a high realization for the measured theta 1 implies also a high realization for the unmeasured theta 2. And our first result then says that in this class of affiliated covariates, the effect of a new measurement on average effort is completely determined by whether that covariate is an attribute or a circumstance. And moreover, the impact is opposite in the two cases. So measuring a new affiliated attribute reduces effort on average, while measuring a new circumstance increases effort on average. Right, so let me just give you a quick intuition for what's going on here. So we know that in this model, the return to effort is going to depend on the sensitivity of the market's forecast to the realization of the outcome, right? The more sensitive this is, the more valuable it is to improve the realization of this Y. But the market faces an inference problem where the market doesn't know whether a high output is because the worker is truly a high type versus the worker just got lucky. So suppose somehow we're able to create lower uncertainty about theta, right, the type. What that's going to imply then is that the market is now going to attribute variation in Y less to theta and more to epsilon. So this then is going to decrease the marginal value of improving the realization of Y and hence lead to lower equilibrium effort. Suppose in contrast, we were able to instead lower uncertainty about epsilon. Okay. So now it's exactly the opposite. So variations in Y are now going to be seen as more reflective of the type, less reflective of a random shock. Okay. Or put another way, you're going to be better able to debias the signal Y, and hence it's in a way a more informative signal about theta. So now the marginal value of improving Y is going to go up, leading to higher equilibrium effort. Right, so it might be tempting then to just say, well, attributes are informative about theta, circumstances are informative about epsilon, so new attributes should lead to lower equilibrium effort, and new circumstances should lead to higher equilibrium effort. Okay. Now, what that misses is that what measurement of a new covariate implies for ex post uncertainty about these two random variables is not straightforward. Right, so let's consider, for example, measurement of theta 1. There is a direct effect from that, which is that theta 1 is now known. And taken alone, that's got to imply lower uncertainty about theta. But there's a second indirect effect, which is that if these two attributes are correlated, then conditional uncertainty about theta 2 may actually be quite large at some realizations of theta 1. In fact, it can be so large that actually uncertainty about theta increases at those realizations of theta 1. And that then leads to higher value of effort. And by the way, we don't actually know exactly how much higher, because the marginal value of effort is in general a complex nonlinear function of these beliefs. Okay, but it'll be higher. And this is exactly what we saw in the example, right? So here you can think about these two as two different realizations of theta 1. And in one case, we had lower uncertainty about theta, and in the other case, we had higher uncertainty about theta, even though it's an attribute in both cases. All right, so the previous result then says that when a covariate is affiliated, indeed, this indirect effect can lead the direction of impact to differ across agents. But on average, it's got to be the case that the aggregate effect follows the same direction as this direct effect. And the next result then further clarifies these two forces by just shutting down this redistribution of uncertainty part entirely. So formally, that's going to look like this condition. Right, so we're going to say that attribute 1 satisfies strong homoscedasticity if this random variable, which is theta 2, okay, the unmeasured covariate, minus the expectation of theta 2 given theta 1, if that random variable, which you can think of essentially as a sort of d-meaned residual, if that's independent of theta 1. All right, so you might remember that in econometrics, homoscedasticity is a condition in regression models that says that the variance of the residual term is independent of the realization of the covariate. And here what we're demanding is that it's not just the variance, but in fact, all higher moments, and in fact, everything about the distribution, all of that has to be independent of theta 1, except that we're allowing this expectation to potentially depend on theta 1. Right, and so naturally, this imposes a pretty rigid structure on how the covariates may be correlated, but it's one that we find interesting still because it accommodates a number of canonical cases. So multivariate normal covariates corresponding to multivariate normal theta and epsilon, that's a parametric family that's assumed really in much of this literature following Holmstrom. And then moving beyond the Gaussian case, anytime we can decompose theta 2 into theta 1 plus an independent x, that again is going to satisfy this condition, because whatever the realization of theta 1 is, that's simply going to lead to a translation in your beliefs about theta 2, but the spread of that belief is going to be independent of theta 1. All right, so then our second main result says that the previous directional change in average effort manifests as a stronger uniform effect in this class of strongly homoscedastic covariates. So if an attribute satisfies this property, then measuring the attribute reduces every agent's effort, in fact, actually by the same amount. Whereas if a circumstance satisfies it, then measuring that circumstance increases every agent's effort, and actually again by the same amount. Right, so in this environment, we can't see disparate impact. And so when this condition fails, then we would expect the magnitude of effort change to potentially differ across agents, but we can still interpret this as a limiting case where the redistribution of uncertainty across agents becomes small. So potentially the magnitude may differ, but at least the sign should be the same across agents as long as this force here is not too strong. Okay, so now let's take these positive results about how measurement of new covariates impacts effort, and let's go back to this initial question about what a regulator might want to do. So specifically, let's suppose measurement of some new covariate has become available for forecasting, and a social planner gets to decide whether the market is actually going to be permitted to use this new covariate. So here, we're going to measure surplus generated by a given agent with type theta and effort E to be the expected output of that agent minus the agent's cost of effort. And then for any family of measured covariates, JK, we're going to take aggregate welfare to be the expectation of this social surplus across agents. Okay, where now E star is going to be a random variable. So this is equilibrium effort. It's a random variable whose distribution follows that of the distribution of effort across agents in the population. Okay, where again, these agents may have varying covariate values. And our main result here says that attributes improve welfare, improve this aggregate welfare, if and only if the reputation weight beta is sufficiently high, while circumstances improve welfare if and only if the reputation weight beta is sufficiently low. So just to remind you, the reputation weight beta was this parameter moderating how much the agent cares about the second period reputational payoff compared to the first period cost of effort. And then, so formally what our result says is that for any baseline family of measured covariates, JK, and for any affiliated or strongly homoscedastic attribute that's outside of this baseline class, there is a threshold beta star such that measuring that attribute improves welfare if and only if the reputation weight exceeds that threshold. Whereas for a new circumstance, there's also a threshold, and measuring that new circumstance is going to improve welfare if and only if the reputation weight is less than that threshold.
Annie, 2 minutes.
Okay, thank you. Right, roughly speaking, the intuition here is that attributes reduce effort. So if effort begins inefficiently high, which corresponds to this beta being very large, then that's the case where the attribute has an opportunity for improving welfare. Okay, circumstances increase effort. So when effort starts out inefficiently low because beta is too low, that's the case where the circumstance has an opportunity to improve welfare. Of course, that's all really slipping under the rug, all the distributional consequences of measurement of a new covariate that we spend a while discussing, right? Disparate impact and all of that. And so what the result says is that those distributional details don't matter for this qualitative result. However, where it ends up playing a role is in determining the sizes of these thresholds. So in particular, note that in the affiliated case, it's actually possible for beta star to be equal to 1. If beta star is equal to 1, then this condition is vacuous. So it may actually be that the attribute never improves welfare, even for arbitrarily high reputation weights beta. And so in the paper, we have a result that says that if attribute J prime does not produce disparate impact, that's a sufficient condition for beta star to be strictly less than 1, meaning that the attribute does improve welfare, at least for large enough beta. In contrast, if disparate impact is sufficiently extreme, then it can be that beta star is equal to 1 so that the attribute actually never improves welfare. And this is not just a purely theoretical case. So actually in the previous labor market example that I showed you, there it is indeed the case that disparate impact is so stark that measurement of residential stability decreases welfare for every possible choice of beta. So then the takeaways here are that for small reputation weights, the regulator should ban attributes. For high reputation weights, the regulator should ban circumstances. if disparate impact is sufficiently extreme, then again, the regulator should at least tend in the direction of banning the covariate. And let me just note, by the way, that this third effect happens even though we haven't actually explicitly built into the social welfare criterion any consideration of inequality, right? We're simply looking at expected social surplus. We didn't program that condition to care about distributional concerns. Nevertheless, that emerges endogenously.